Saxon Algebra 2, this is Lydia's final recap. Lydia, as we discussed, I just want to go, you did a fantastic job on your final. Let me start by saying that. You did a fabulous job on your final. You did a fabulous job in the class. Your grade, I haven't calculated yet, but I'm sure it's a nice A. And what I learned about you, Lydia, is that you operate out of joy. And if you can find joy in something, my observation is, this might not be how you feel about yourself, but my observation is that when you find the joy in something, you're super motivated to keep at it. And I think that is a lovely quality to have. And my experience in life is that you can find joy in just about anything. So, yay, because that means that anything you undertake in life, you'll always keep working until you get to that point where you find the joy. And I could see you find the joy in your math. So I celebrate that. You did a great job. You don't need to do any extra work in algebra to earn your grade or to convince me that you are a really strong student and a fascinating person. This is a gift I want to give to you. I don't want you to end your math career going, I did all right, but those last few problems on the final just killed me. I don't want you to walk away with that. I want you to walk away with a sense of, yes, I killed it 100%. So that's why I just want to review these 3 problems, 2 on the final and 1 of the review problems that got the better of you, at least in the moment. We'll review those. I want you to just go over maybe 1 or 2 more problems, and then I will have you retake those problems, not to change your score, because like I said, your score's fine, but just so that you walk away with that strong sense of nailing it. Okay, so there are 3 areas we want to talk about. The first one was on the final, and it was question 4. Which worked from lesson 111, and I think I know what happened in this. This is one of those 3 statements of equality problems. You did the first two problems just perfectly. I'm trying to think. Yeah, this is a different one. This problem looks a lot like the one that was on the test, but it is slightly different. There were 16 nickels, dimes, and quarters whose total value was $1.50. Okay, these you got fine. You said the number of nickels plus the number of dimes plus the number of quarters equals 16. And then you went ahead and multiplied 5 times the number of nickels plus 10 times the number of dimes plus 25 times the number of quarters, the value of each coin, equals $1.50, and you knew take out the decimal and leave it like that. So it's all in cents and not in dollars. That way we don't have to deal with the decimals. Okay, you nailed that. Here's where you got into trouble. It was the third one. The question goes on to say how many coins of each kind were there if there were 3 times as many dimes as quarters. And you fell into the trap, I'm sorry to say, 3 times as many dimes as quarters. Your brain tried to do that to you. No. Let me read it again. There were 3 times as many dimes as quarters. Where we start with that is by writing the inequality. There's more dimes than there are quarters, right? There are 3 times as many dimes as quarters. So if you write the inequality first, it helps you see, oh, we have to multiply quarters times 3 in order to bump it up to how many dimes there were. If you start with just the equal sign, it's really easy to get it wrong. But if you write the inequality first and recognize, yeah, I've got more dimes than quarters, so I've got to multiply this one by 3 in order to get it to work. This is the trap that you suffered. So always write the inequality first. And then fix it using that other piece of information. This is a really common mistake. It's a big trap that you fell into. Many other students have too. Okay, and then from there you can go on to solve the problem by substituting dimes. And I'll go ahead and work it, but I think this part probably wasn't what tripped you up. Okay, so these are my 3 equations that I'm working with. This one is the one I like. So what I'm gonna do is I'm gonna substitute this one into these two so that I'm down to two variables. So it's gonna be n plus 3q plus q equals 16, and 5n plus, oh, this should be d. Sorry, I wrote that wrong. 10 dimes equals, so it's 10 times 3q plus 25q equals 150. Yeah, so we substituted that in. Now we'll clean this one up and then we'll eliminate them. We'll clean them both up and then we'll eliminate them. So this becomes n plus 4q equals 16. This is 30q now. So 5n plus 30q plus 25q would be 55q equals 150. Okay, let's multiply. So now we're going to eliminate these two. And again, I think you probably have this part. You just got waylaid up there. Let's multiply this one by minus 5. We'll cancel at the ends. So then we have minus 5n minus 20q equals, let's see, that would be 80, minus 80. Okay. I'm just going to look at my solutions guide to make sure that I'm not going off the rails here. 117. Yes, we're in good shape. Okay, I was just looking to see what John was doing. He's off on a different, he has these two the same, and then he goes off in a different area. Okay. So we multiplied this one by 5. Now we're combining these two to get 35q equals 70. Yay, John. Divide by 35. We get q equals 2. And then we can get the number of dimes, because it's 3 times the number of quarters, so that would be 6. And then they have to add up to 16. So the number of nickels must be what? 8, right? Double checking with John. 8 nickels, 6 dimes, 2 quarters. Okay, so that is the right answer. Like I said, I think this is fine. You just went haywire here with that equation. So that is lesson 11. It was question 4 on the test. This problem's really similar to what we had on the test. Okay, that's lesson 11. The second problem on the test that you had an issue with was question 6, and that related back to lesson 5, word problems. Now, I apologize for any miscommunication or misunderstanding. I thought we were working to go back in and fill in your missing knowledge, and you were working under the understanding that you never had to go, that you didn't need to go back and fill those in, that you could just continue to skip over those problems. So I apologize for that. I considered dropping this question for you because of that misunderstanding, but I did put this lesson on the study sheet. So that was a flag that we were going to include it. So I decided to leave it and let this be a learning opportunity so that you could go back and learn to do this problem, because obviously I think it's important if I carried it forward through the whole year and said, yes, we need to do more of these. 5-4. Okay. So I'm going to teach this to you as if we were doing it the first time. I'm going back to problem set 5, 4. Okay, so this is back on page 41. Oh, so cute. 1/8 1/8 of the clowns had red noses. If 12 clowns had red noses, how many clowns were there in all? Okay, here's a way to diagram these problems that is super helpful. Here we have some clowns. All right, we're dealing in fractions in this thing, so that represents the full group. There's a number of clowns. We don't know how many it is, but we do know that we can divide this group. And some of the clowns will have red noses. We're separating them into a group, and then the others don't have red noses. Okay? Now, the way I tell students to think about this when we're imagining it is, imagine you're looking down at a round room. When I lived in the dorm, the center part of the dorm was round, and then the two wings were like half circles on either side, and then they were connected in the middle. And we always called this round space the kiva, which is, I think it's a Native American word that means a round ceremonial room. So anyway, that's what I think about. But you're imagining this round room, and you're seeing all these clowns standing around in the room. You don't know how many, but there's a bunch of them. We're looking down at them, and those are the tops of their heads. And then you shout down on a megaphone, and you say, all clowns with red noses move to the north end of the room. All the clowns who don't have red noses move to the south end. And you get them to move and separate into these two groups. Now, I've just arbitrarily drawn my line here. I don't know if that represents a good proportion of the red noses to the non-red noses. You know, if you think about dividing this into half or a third. I just guessed and put the line in wherever I thought. We're gonna let the math tell us the numbers, but imagine them separating like that, and then somebody comes in with a ribbon to divide off the red-nosed clowns from the non-red-nosed clowns, and that's what that line represents. 1/8 of the clowns had red noses. Okay, so we can write that right here. 1/8 of them. That doesn't tell us how many clowns. We still don't know anything about how many there were, but we do know that proportionally, excuse me, there were 1/8. Now, we can use our own brains to calculate that the ones that don't have red noses must represent 7/8, because it has to add up to 1, right? Okay, if 12 clowns had red noses, okay, so now we know there are 12 here. How many clowns were there in all? So I'm gonna put an X here because that's what we want to find out. Okay, does this make sense? You don't have a chance to say no if it doesn't, I'm sorry. So we have a formula that will work for this. Second, I meant to make that big. This is our formula. It's called a fractional groups formula, and it says if you take the fraction and multiply it by the total number, which is often represented in a word problem by the word of, then you'll get a special group. And that is often represented by the word is. So even though these little words seem kind of random and arbitrary to be shoving in a formula, it makes sense because most word problems use that. So what we're gonna do is we're gonna use this little formula and calculate how many clowns there are. The fraction of clowns that have red noses is 1/8. If we take 1/8 and multiply it by this total group, which we don't know what that number is, we will get the special group, which is 12. See how I did that? The fraction times the total group equals the special group. So this will allow us to calculate what that number is. To solve it, I'm multiplying by a fraction. So my first instinct is to divide by a fraction, but I go, I don't want to divide by a fraction. That's just scary and wrong. I would rather multiply by the reciprocal, because that will make this fraction go away too. And I have to do it on both sides. 8 over 1. I don't really need the over 1, do I? Because that'll be the same. This cancels. X equals 96. So that tells me there were 96 clowns in all, because if I take 1/8 of them, that will give me the 12. Now, the other question is, how many are here? There's two ways we can find that out. These are the red noses. and these are the not read. The long way to find this out is to say, okay, I can use this same fraction or this same formula to solve for that. This time I know my fraction is 7/8. And I know, this time I know my total group, 7/8 of 96 in all, I'll put that over 1 in a fraction, will equal that number. I'll call it y. Okay, I could do it that way. But the even easier way is to say, okay, if there's 96 in all and 12 have red noses, then I can just do 96 minus 12. Let's do it both ways. 4, 8, and let's double check with this way using the formula. 88 goes into 96 12 times. 7 times 12 is 70 plus 14, so it's 84. Same number. Does that make sense? There it goes. So this formula is super helpful. These diagrams are super helpful in learning, in arranging the information. Let me do one more. Let me say one other thing about the problem on the test that was super tricky. We have to be careful when we're using the formula to use, if we're using information here about the special groups, we have to make sure that we know which special group we're going after. One problem students have is they might say, oh, the special group is 12 and the fraction is 7/8. No, these two don't go together. If you're talking about the 12, you have to use the 1/8. If you want to talk about 7/8, then that's the number that goes with 84. So you have to be careful when you're using this data to fill in the formula that you use the matching data. And the problem that we had on the test about the squatters confuses that issue. It tries to get you to mix up. I believe that one is 2 steps, where we first have to fill in this information and then we go back and fill in this one, which is what we did here, down here. So you practice that. But be very careful about that when you're doing these problems, that you're gathering information about the same special group, the fraction and the number. Depending on what John gives you in the problem, there's different ways that that information can be provided, but just remember which part of the special group you're dealing with. Okay, let's do one more of these problems. John likes to make really kooky examples. The one about the squatters is a good example. This one, which is lesson 5, problem 5, is another example. 5/7 of the Tartar horde, I'll write that down so you can believe what I'm saying. Yeah, the Tartars, right? They were in Eastern Asia, weren't they, like the dudes that ran around on the steppes of Russia? And the horde, they were galloping around on their horses. 5/7 of the Tartar horde rode horses. If 140,000 were in the horde, how many did not ride horses? Okay, so before we deal with numbers, we just try to get our head around this crazy story. Here's our Tartar horde. There they are. We're dealing in fractions because it said 5/7. So this equals 1. This is the whole group. Now we're going to take that Tartar horde. They're in our Kiva room. And we're saying, okay, all of you who were riding horses that day or are riding horses now, step to this end of the room. And so this is the ride horses group. This is the special group that rides horses. And John tells us that was 5/7 of the group. So that tells us that it's 2/7 that didn't ride. Okay, maybe they rode Vespas, maybe they rode Ferraris, maybe they rode on St. Bernards. We don't know. We're just dividing them according to one trait. Okay, so we've got the fractions worked out. If there were 140,000 in the horde, okay, that means the total group. 140,000 were in the total group. How many did not ride horses? Okay, if we hadn't filled this fraction in, we would be confused right now because we'd be thinking, okay, we've got information about the special group and we've got information, or the total group, and we know about the horses, But we want to find the other part of the groups, the special group. We don't want to know about the part that ride horses. We want to know about the part that didn't ride. If we didn't have the inkling in the back of our brains that we can find the fraction rather, not the percent. If we can find the fraction that didn't ride by using this, and the idea that this represents the total, then we would be in trouble. This is an important piece of information, and I just automatically fill that in. If I get one fraction, I write in the other because I know it will be helpful to me. The goal is to fill in all the different parts of this diagram. Okay, so we want to know how many didn't ride. So the way we do that is to use our formula. F times of equals is. And again, this represents the total group, and this represents the special group. Okay, so our fraction of the special group we're interested in is 2/7. The total group is 140,000. I'll put it over 1. Equals the special group we want, we called X. Make sense? So we don't really care that much about the group that did ride horses in this problem. It's just really helpful to know what their fraction was, because then that gives us information about our group. Okay, this goes into this, 20,000 times, right? Because 7 into 14 goes twice, and then all the zeros stay the same. And then when we multiply it out, we get 40,000 didn't ride. I'll put it over here. And then that allows us to figure out how many did ride. We could either do it with the fraction and use the formula, but we can just subtract, and it's super easy in this problem. And so then that tells us that 100,000 did ride. I'm just double checking our answers. Oh, I have to go back in the archives. Let me just double check before I move on. I'm sure those are right, but you know what? Pride goeth before a fall. 40,000 hordes didn't ride. And that's what we got. And then the clowns. I didn't mark the clowns. 96 clowns in all. That was what we were trying to find. 96 clowns. Whenever you're working a problem that has words, please always put the unit or the description of what you've calculated in your answer. If there are words in the question, you should have words in your answer. I'm not a huge stickler over that, but many college professors are. So train yourself, well, now you're almost ready for college, sorry, but that's really important. Please put a special emphasis on that. If there are words in the problem, put a word in your answer. That's a good rule of thumb. Okay, that is my review on lesson 5. Honestly, this one you probably need to review a lot more than you need to review the 3 statements equality, the one you did before. So I would suggest, and the other thing is that there are so many variations on these problems can make, because look, we have 1, 2, 3, 4, 5 pieces of information, and that can vary. We can also change this to be about decimals or percents, and that's really confusing. Although the one on the test, let me just double check. It's problem 6 on the test. The one on the test is a fraction. So don't worry too much about the ones that use a decimal or a percent to divide the groups. They work the very same way. It's just using decimals or percents instead of fractions when you do your calculation. But the one on the test is fractions. So focus and don't worry about the exceptions to the rule. All right, if you have any questions about this, of course, ask me. The last thing I want to review with you was actually a review problem. It was the one for 427. So that was the middle of the 3 review problems. And it's about permutations, which was lesson 116. The fun thing about permutations is the same thing that gives you a headache about permutations. Every problem has a slightly different feel to it, and you can't globalize. There isn't one simple formula or way of thinking about them that you can kind of copy and paste from problem to problem. You have to look at each problem with fresh eyes and logic it out based on the way the problem is written, and that's what makes it hard, and that's what I saw happening in your work, is I felt like you were taking a process that had worked in another permutation problem, and you were trying to apply it to this one, and no va, it didn't work. So I'm flipping up to lesson 117. I'm gonna do problem 117.6. This is a hard one that's a little bit different than the one on the test, but it'll just give you an idea. Rosabelle has 5 different flags and 8 flagpoles in a row. How many different ways can she fly her flags if she flies all 5 flags every time? Now this is confusing because we say, should we look at the flags or should we look at the flagpoles? Well, if we look at the flagpoles, that's way harder because some of the flagpoles are going to be empty, and that's hard to imagine how we're going to draw the boxes. So let's look at the flags themselves. Let's look at what she's going to do with each flag. There are 5 of them, so I'm going to make 5 boxes. Those actually turned out fairly even, right? So she has her 5 flags over her arm. She walks out to her yard, I guess. I don't know where she has all her flagpoles. They're in a row. So she walks up to the first one. No, she's standing there and she says, which flag pole shall I hang my first flag on? There are 8 flag poles. So she has 8 different choices that she can make. Now, it would be fair to assume she could hang multiple flags on each flagpole, but that's overthinking. We're imagining she's only going to hang 1 flag on each flagpole. So once she hangs the first flag on one of those 8 flagpoles, she only has 7 left to choose from. John doesn't tell us, oh, there's no replacement in this, but we know physical objects, you can't just snap your fingers and get another flag out of the air or another flagpole. So we're dealing with physical things. So we know that when she goes to hang her second flag, she doesn't have 8 flagpoles to choose from anymore because she already hung 1. Now she has 7. Make sense? When she goes to hang her third flag, there are 2 of her flagpoles are already used. So now she just has 6 and then 5 and then 4. John doesn't tell us, oh, there's no replacement in this, but we can logic that out just by thinking about the way that flags and flagpoles work. So we know there's no replacement. That's the math phrase we use. But that we know that there's a limited number of flags, of flagpoles, and we can't just conjure up new ones out of the air. The tricky part of that is you could hang more than 1 flag on a flagpole, but we're not going to make that assumption. All right, if you multiply those all together, you get 6,720. That's not the important part to me. This is the important part. Okay, so this one, what this problem gives us a really nice example of is how we have to use common sense sometimes to deduce what's going on in the problem. Now, there is another problem that I recall from the homework. I don't have the reference on it right now, but it was about license plates. And this one is a really good illustration of how the problem can be worked in 2 different ways depending on what John tells us. This license plate problem says that there were 3 letters and then 3 numbers in the license plate, which is pretty typical, right? So in the first 3 parts, you could have letters, and in the second 3 parts, you had to have numbers. Okay, what that tells us is we have to think differently about these 2 sections of the license plate. If we're choosing letters, how many letters do we have to choose from? Well, we are thinking about the alphabet, and there are 26 letters. John doesn't give us any rules about, oh, you can't use O's or you can't use L's or anything like that. So we assume we have 26 letters to choose from. He doesn't tell us, I don't believe, maybe the actual problem does, but let's assume now that here we're allowed to replace. Okay, so for example, we could have the AAA as the letters here. It's okay to use the same letter again. So when we go to calculate the permutations, we know that we can use any one of those 26 letters in each of the first 3 slots. Okay, so we've taken care of that. Now we have to switch over and think about numbers. In these next 3 slots, we have to put not a letter, but a number, a digit. How many digits do we have to choose from? Okay, there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 digits. Students get topsy-turned over this because it only goes up through 9. So they think, oh, we have 9 digits. But 0 is a digit too. So we have 10 digits in our system. And so that means, assuming there are no rules about you can't use a 0 or something like that, we have our choice of 10 digits for each of those. All right? So that's if we work the problem with replacement. We're understanding that it's okay to duplicate them. But what if John changed it and said, no, actually, we can't replace. We're not going to have any of the same letters, and we're not going to have any of the same numbers. So this is without replacement. Or sometimes John will use the word repetition, which means the same thing. Replacement and repetition, right? The idea is that either you can repeat them or you can't. And in this one, we're saying you can't repeat them. So now we go back and we say, okay, 26 for the first one, but now we can't use that letter. So now it goes down. And then same for the digits. The first time we have a choice of 10, but now it goes down. This problem is a good example of one where we need to have a rule because the problem itself doesn't inherently rule out the idea that we could either replace or not replace. It's different than a flagpole, which is a physical thing. These letters that are being built into the license plate, there's no reason why we couldn't have 3 A's in a row. But maybe that's, a state law or something. Who knows? So we need to look to John's rule in some problems, but in others, he might not even tell us because it should be, quote unquote, should be self-explanatory. So that's what's tricky about these permutation problems is there aren't hard and fast rules, and you really have to be on your toes and thinking through each problem logically in order to get the right combinations of things. It doesn't always count down. It doesn't always stay the same. They're tricky. So try a handful more of these problems, and then we'll go back to the one on the test. Let me see if there's anything I want to tell you about the one on the test. Oh, it was a review problem, wasn't it? It wasn't actually on the test. The problem that is the review problem is very straightforward about what you can do and what you can't do. It's like this rather than this. It tells you specifically what the rules are. So, yeah, try a few more of those and see if you can kind of get the flow of how they change. Please ask me if you are still frustrated and struggling with them. Okay, Lydia, that is the end of your review. I will be in touch.